You know that feeling, right? You're staring at a math problem and you can just tell it's going to be an absolute slog to get through. Well, today we're going to look at a beautiful little cheat code for mathematics called Euler's theorem. It's this incredibly elegant shortcut that can take a total calculus nightmare and turn it into something surprisingly simple. And that nightmare, well, it looks a little something like this. Yeah, just take a look at this beast. If you've ever taken multivariable calculus, you know what a pain this would be to solve directly. Finding all those second-order partial derivatives, multiplying everything out, adding it all up, my hand is cramping just thinking about it. It's exactly the kind of problem designed to make you sweat. But what if I told you there's a way to solve this in just a few lines without actually calculating a single one of those messy derivatives? Let me show you how it's done. Okay, so let's think about the direct path, the brute force method. You'd have to find the partial derivative of u with respect to x. Then you'd have to differentiate that again to get the second derivative. Then you'd do the whole thing all over again for y, and then you'd have to find the mixed partial derivative. It's long, it's tedious, and honestly, it's just packed with places where one tiny slip-up can ruin the whole thing. But this is where the real beauty of math shines through. Instead of just grinding through the calculations, what if we took a step back? What if we looked for a deeper structure, a hidden pattern inside the function itself? It turns out there is one, and it's the key that unlocks a massive shortcut. So what is the secret pattern? It's a property called homogeneity. Now, I know it sounds a little intimidating, but the core idea is actually super intuitive. It all comes down to how a function behaves when you scale its inputs up or down. So here's what it means. A function is called homogeneous if, when you multiply all of its inputs, like x and y, by some factor t, the entire output of the function gets multiplied by that same factor raised to a specific power. And that power, n, is what we call the degree of homogeneity. It's the magic number that's going to unlock everything for us. Let's make this really concrete. On the left, we've got a homogeneous function. See how when we plug in tx and ty, we can neatly factor out a t squared, and we're left with the original function right there beside it? Perfect. But now look at the function on the right. That single y term messes everything up. When we substitute, there's no way to pull out a consistent power of t. So the function on the left is homogeneous, but the one on the right is not. And this brings us to the hero of our story, Euler's theorem. This is the amazing tool that's specifically designed to work on these special homogeneous functions. This is our key. This is the shortcut. What Euler figured out is just genius. He realized that if a function has this special scaling property, then there's a direct, predictable link between the function itself and a certain combination of its partial derivatives. He wrote this relationship down in a simple but incredibly powerful formula. And this is it. This is the core idea. It says, if you have a homogeneous function u, you can take its partial derivative with respect to x, multiply by x, then add that to its partial derivative with respect to y, multiplied by y, and the result is just the original function u multiplied by its degree n. It's a direct link. No more messy calculations. Okay, theory is fun, but let's put it to work. How do we use this elegant theorem to solve that monster problem from the beginning and avoid all that tedious differentiation? All right, here's the first clever move. Our original function u isn't actually homogeneous because of that logarithm wrapped around it. But that's okay, we can fix that. We can do a little algebraic jujitsu. If we take the exponential of both sides, we can get rid of the log and create a new function, which we'll call z. Now this new function, z, is the one we can apply the theorem to. So next up, we need to find that magic number, the degree n, for our new function z. There's a classic trick for this. You just factor out the highest power of x from the top and from the bottom. So on top, that's x squared. On the bottom, it's just x. You simplify x squared divided by x, and you're left with x to the power of 1. And there it is, just like that. The degree of homogeneity, our magic number n, is simply 1. That's the key we needed. That little number unlocks the rest of this puzzle. Now we're ready. We can apply Euler's theorem. But remember, the crucial step here is that we have to apply it to our nice homogeneous function z, not our original u. So the theorem tells us that this combination of partial derivatives of z is equal to n times z. Since n is 1 and z is e to the u, we get 1 times e to the u. Now for the really elegant part. We have to connect this all back to our original function u. Since z equals e to the u, we can use the chain rule to find the derivatives.
And when we substitute those back into the equation, we get an e to the u term on both sides. And you know what that means. They cancel out perfectly. Gone. Leaving us with this incredibly simple and beautiful result.
Okay, take a breath. That's a fantastic result. But we're not quite done yet, are we? Remember the original question. It was asking about those gnarly second-order derivatives. So how do we get there from here? Do we have to start all over? Absolutely not. We're going to build on the answer we just found.
The strategy is incredibly clever. We're going to construct our final answer piece by piece. First, we take the simple result we just got and we differentiate the entire thing with respect to x. Then, we multiply that whole new equation by x. Next, we do the exact same thing again, but for y. We differentiate our result with respect to y and then multiply that by y. This creates the exact terms we need.
Okay, so this process leaves us with two new equations that honestly look kind of messy on their own. They don't seem very helpful by themselves. But the final piece of the puzzle, the real magic trick, is to see what happens when we just add them together.
And would you look at that? When we combine everything, the exact expression from our original nightmare problem just appears. It's right there on the left. We also have this extra bit tagged onto the end. But wait a second. That looks really familiar, doesn't it? Yes, that's it. That extra term is the exact first-order result we already found just a minute ago. We know that entire expression is just equal to the number 1, so we can substitute that value right into our equation. It's like finding the final piece of the puzzle. And with one final, super simple step of algebra, just moving that 1 over to the other side, we have our answer. That entire, terrifying, complex expression simplifies all the way down to -1. We did it. No messy derivatives, just pure logic and a beautiful shortcut. So what's the big takeaway here? I mean, what's the point of all this, beyond just being a really cool trick to have up your sleeve for an exam? Well, the crucial idea is that by identifying an underlying pattern, that property of homogeneity, we were able to use a powerful, specialized tool that let us bypass all the tedious work. And that concept, the idea of stepping back, finding the hidden structure of a problem, and then choosing the right tool for the job, that's one of the most powerful problem-solving techniques there is, not just in math, but in everything. And that leaves us with one final thought. This principle applies far beyond calculus. Whether you're coding a program, analyzing a financial market, or even just trying to solve a problem in your daily life, the most elegant and powerful solutions often come not from brute force, but from seeing a hidden pattern that everyone else missed.